Clinker Factor, the cement industry podcast.
Welcome to the Clinker Factor, a podcast from WCA which looks at the cement industry's response to climate change around the world and other topics of interest. I'm Ian Riley, CEO of WCA, and your host on the Clinker Factor. Before we get started, I want to draw your attention to the 2023 WCA Annual Conference, which will be held on October the 24th and 25th at the Emirates Towers in Dubai. Super early bird tickets are available until June the 30th, and we still have a few exhibitor slots available. So we'll put a link to the registration website in the episode notes. So today I'm talking to Hari Harikumar, who's VP and General Manager of Advanced Carbon and Membranes at CHASM Advanced Materials, a company which develops and manufactures carbon nanotubes. So Hari, perhaps we can start by introducing yourself and telling us a little about how you ended up being connected with the cement industry.
Hey, thank you very much, Ian. And it's been a pleasure always to be associated with you and WCA in general. So CHASM as a company, we are a startup, though technically we started quite some time ago as a company applying nanotubes to various applications, as well as manufacturing nanotubes for various applications. And the products we productized were primarily in the automotive industry and the electronic industry, widely called the printed electronics applications, where we have real breakthrough products like transparent heaters and transparent antenna, which are right in trend with the new cars, automatically driven cars, as well as 5G kind of communication. And so a few years ago, the company started to look at, we started to go into films. How about additives? And how about grow our space in additives? And around that time, we did a joint venture with another company to make an additive for specialty applications like plastics and batteries. And then we started looking at what are the other high volume additive markets, and we came into the cement industry. And that's how we kind of got into the cement. And thanks to one of our academic partners, she had already from University of Texas at Arlington, they had already applied nanotubes to a bunch of cement applications. And we started to learn about how can we get in and what challenges the industry would have to adopt this material, and how can we be the forerunners in breaking those barriers.
So as you said, carbon nanotubes have been around for a while. What were the barriers to getting involved in using them in the cement industry?
Cement, as you know, is a very cost-sensitive industry and at the same time very, very technical. And so if you have to make a difference, you have to have substantial performance gains and be relevant to cement manufacturing and cement's commercial positioning. And so though the CNT or nanotubes or carbon nanotubes were known to show performance, but however, when it came to scale and came to commercialization in an industry like cement, it was a no-no. And hence we looked at the problem from, in fact, literally the company is called CHASM for that reason, where we attack a problem from both ends, not just from the laboratory end of the side, but also from the market side, and then bridge the chasm. And so we started to look at what should be our commercial positioning, how should we break down the cost of nanotube. And a great element which our co-inventors in our company did is to pivot to what is called a rotary kiln reactor to make nanotubes as compared to the fancy fluidized bed reactors. And what it does is it makes it very scalable, capital light, and brings costing now down from hundreds of dollars per kg for multi-wall nanotubes to now tens of dollars per kg. And now you are in the cement ballpark. And with an additive requirement of hardly 0.15 to 0.1 to 0.15%, which means you're talking about 1 kg of additive for 1 metric ton of binding material. So now you are very much in the ballpark. I mean, a typical marginal cost of cement manufacturing is around $50 a ton. And now if you're adding a kg of nanotubes to it and you're in tens of dollars per kg, you are now in the ballpark. And that was a major breakthrough from a manufacturing standpoint. And the second barrier was dispersion. Nanotubes are really, really small, as one can imagine. And so they like to stick to each other because they have very high surface area. They like to stick to each other. So unless you disperse them and make them stick to the cement particles, they will not really provide any good results. Now, the methods of dispersing used in academics all the while has been pretty high energy, ultrasonic, and water, and so on. And if you even look at it, you will say, wow, this cannot be going to market the way it is. You cannot be shipping tons of water around the world. So you can't be using so much of ultrasonic energy. So we have to do something to it. So dispersion was a major barrier, and we pivoted into two major innovations. One was to micro encapsulate nanotubes into polymers, which can almost be like a dry additive, like a drop-in in a cement plant, in a concrete facility. And that's something we are developing further with multiple chemistries in it. And other major breakthrough, which might even take it faster to market, is a direct deposition of nanotubes on cement, a complete dry process. And these two inventions makes us very unique, and nobody else has done it. And in fact, given academically, people haven't done it. And the simple reason is people who are making nanotubes never applied it to cement. And people who are applying it to cement, like the academic and the research community in the major OEMs, were not making nanotubes. So there was no bridge between the two, and they were using liquid as a means to disperse. And as we were attacking it from both sides, we said, hey, why don't we overcome this whole liquid thing and try to do what is fit for purpose nanotubes as compared to a cookie cutter nanotube? And that allowed us to kind of break this barrier.
So let's come back to dispersion in a second. But before we do that, could you explain what the carbon nanotubes do when they're used in a concrete mix? So what is the performance that they're giving to the concrete?
Yeah, thank you for bringing that up. So by adding 0.15% or 0.1 to 0.15% of nanotubes to cement, in say, for example, when you perform a mortar test, it beautifully increases all three elements. Stiffness, which is Young's modulus, it increases compressive strength, and it increases flexural strength. And as you might know, in most additives, when you add, you will not go high on all the three properties. One of them you will compromise, whereas nanotubes tends to pick all the three up. And so let's start one at a time. Let's talk about compressive strength. So the nanotubes tend to, and there are a lot of theory papers in it and various schools of thought, but the proof is in the results. It tends to go closer to the surface of the cement particles and provide early surface areas for hydration, and thereby increasing the 3-day compressive strength as much as 30% above baseline, 30 to 40% above baseline. And that's substantial. And the 28-day strength also goes up by around 15 to 25%, depending on various forms of nanotube and proportions of nanotube. So compressive strength short term as well as the 28-day goes up substantially. Stiffness goes up 50 to 80%. Young's modulus goes up in mortar level. Now, of course, you know that not everything in the mortar level will translate to concrete. Especially stiffness is less likely to translate, but however, it's still a useful number that the Young's modulus goes up substantially. And third, which is, when I was new to civil engineering in my grad days, people used to say, if concrete is in tension, civil engineers are in tension. And which is why flexural strength in concrete is always a big challenge. And interestingly, nanotubes increase flexural strength by 70 to 100%. And that is primarily because it's providing nano level reinforcement between the CSH or the hydration points, and thereby providing that extra tension push. And this is substantial. And if you use these three elements, compressive strength, of course, you can reduce clinker substantially. The flexural strength, one should also look at how do I change the design of things like pavement and so on to reduce steel and thereby reduce the embodied carbon in the structure. And so it opens up those avenues as well.
And so coming back to the dispersion then, why is dispersion a challenge? Is it simply because they're very, very small and they tend to stick to each other rather than sticking to the cement?
Yeah, as the word nanomaterials say, the surface area to volume ratio in nanotubes are much, much, much higher, which is how you're able to take the same carbon fiber or carbon tube, and when you have extreme high surface area to volume ratio, the surface energy dominates the carbon's chemical, strength and so on. And the surface energy becomes a dominant factor. And when you have something with such high surface energy, they will tend to stick to each other as compared to going into the material. And hence, to make them real, like kids, like children is like kids, they tend to stick to each other unless you disperse them, in a classroom as example. So you have to disperse them, and that calls for a lot of energy to disperse them and then lock them where they need to. And academic ways of doing so, were very challenging. The reason is the academicians and other OEM cement companies which are researching on nanotubes would buy pristine nanotubes from people, which are extremely long nanotubes, which are very difficult to disperse, and then use all the energy in dispersing before you deploy and making the whole process not translatable to the industry. And so we had to innovate industry appropriate ways of dispersion, which is fit for purpose in the sense which contributes to cement substantially. And so we had to kind of do an end-to-end optimization as to what is the right length of nanotube to make at the first place so that you reduce the energy of dispersion and increase the properties of the end product, which is nanotube dispersed in cement.
So you mentioned that one way of addressing this was to grow the nanotubes directly on cement particles. Is that right?
So we are not, one can, but we are not, we are growing it in the vicinity of cementitious particles. What is very important is to grow the right size of nanotubes. Nanotubes are conventionally grown on alumina kind of support systems, which are still, again, part of the cement system. So in that way, you have cement system already in growth of nanotubes, but don't grow them, in a way that they are tough to disperse, but grow them in a way that they are easier to disperse and directly goes and sticks to particles like cement. And good thing is once they stick, you cannot take them out, and thereby, it's safe once you kind of put them together.
Right. The nanotubes are providing something akin to a reinforcement at their very small level, at a nano level. So how, when you look at reinforced concrete, how is the performance affected versus, unreinforced concrete? Is there a need for less reinforcement in the concrete? So if you were thinking about it from a whole system standpoint, would you think about reducing the steel reinforcement rather than reducing the quantity of concrete, for example?
A very good point. Extremely good point. So nanotubes seems to influence cement in two ways, okay? Unlike conventional reinforcement. Number one is they are providing surface area for early hydration and even further hydration. So it seems to be not interfering with the chemistry, but provide the right surface area for enhanced hydration. That's number one. Number two, the length of nanotubes are micron level. So the diameters are maybe tens of nanometers. The length of them are 1 to 5 microns as you disperse them in the material. And so they are providing micron level reinforcement. Unlike conventional fibers, which are more millimeter level reinforcement, this is reinforcing at a micron granular level. So as especially under tension or under flexural, as small cracks develop and coalesce into bigger cracks, the nanotube seems to be bridging these small cracks right at their seeding level, and thereby not let them kind of grow and coalesce, or rather extend that life further. So they are not only increasing the strength, but they also kind of provide that internal support for the concrete in tension. And those are the two ways. So there's micron level reinforcement and hydration are the two ways nanoparticles or nanotubes seems to be helping, is the current school of thought. And microscopy also tends to kind of validate that. Yeah.
Okay. Would that have an impact on the way in which structural engineers or designers are using concrete, or will we see basically the same properties, the same type of properties from a concrete that has a nanotube as an additive and a regular concrete?
It's a fantastic question, and it's a good segue too. Conventionally, if you look at regular concrete, there is a clear correlation between compressive strength and flexural strength. So many people don't even measure flexural strength. You just do the compressive strength and kind of interpret the flexural strength as you design, say, thickness of pavements and highways and so on. But now when you have flexural strength going up 70 to 100%, compressive strength is also going up long term going up 20%, short term going up 30, 40%. This correlation, the historic correlation, is no longer valid. And so one should look at flexural strength as it is. And then by plugging in that flexural strength into the design equations, instead of using a correlated flexural strength from the compressive strength, you're bound to optimize your structure within the existing codes of civil engineering codes globally. It is just that you plug in the right strength, flexural strength value, as compared to interpreting the flexural strength from compressive strength. By doing so, the structures are going to be more efficient, or rather, more lean and mean, maybe, and surely less steel, because steel is meant to support the tensile side, and surely less steel, which surely substantially reduces the carbon footprint, and with the possibility of reducing clinker. But as you rightly said, it's about the system level carbon footprint. What is the right thing to reduce? Clinker versus steel versus anything else.
Yeah. So potentially you could have smaller elements doing the same job.
Yeah. Absolutely.
It reminds me a little bit of UHPC, the ultra high performance concrete, which has the steel reinforcement, the chopped wire, steel wire reinforcement inside the material, which also provides very high flexural strength and allows a different approach to design. There's a famous footbridge in Marseille made out of ductile, which is the Holcim brand of UHPC. And it has a span of about 80 meters and a thickness of only 1.6 meters. So you got a 50-to-1 ratio where, normal concrete is only about perhaps 5-to-1 will be the maximum that you could go. So I think it's a very interesting implication there.
Yeah, and it's, the mechanisms of a steel fiber are a little different than the nanofiber. Steel fiber, of course, is pushing the modulus a whole lot, and also providing certain amount of what is called pseudoplasticity a whole lot. The nanofibers, so steel fibers are working at a millimeter level, whereas the nanofibers are now working at micron level. So you're really even coalescing or not allowing the cracks which are at micron size to grow, and thereby, making it. And by the way, you can use them in combination with UHPC. And I've been talking to a few people, but at the same time, our current focus is to be relevant to the mass of the cement industry and also help the UHPC, no doubt, but we want to be relevant to both sides. Yeah.
So can you tell us a little bit about what stage of development CHASM is at? I think you have a pilot plant operating now. How much material can you make from that, and what are your plans to scale up from there?
Yeah, great. And we, in 22, we scaled up from a research reactor. In fact, when I met you in Dubai, that's when we scaled up from a small desktop research reactor to a 50 metric ton per year reactor. 50 metric ton reactor is around 8 to 9 inch tube, which is 10 times the its dia in length, and so that's good enough to make 50 metric tons per year of nanotubes, which is good enough to reinforce 1,000 times that number when it comes to binding material. And so we can make substantial material today for doing trials, and more than small specimens, we can do real life structures as well. But having said that, we don't want to reach a situation where we succeed and then say, guys, wait, we are building a big one. So we want to be ready with our bigger reactor. So now we are building a 1,500 metric ton reactor, which is going to be the world's largest nanotube reactor ever built. And the platform is almost like a 53 feet container. And so it's going to be around 30 odd inches dia, and again, 10 times its length as a length. And, you can visualize it to be literally a container size. So why I'm talking about it as a container is nanotubes are very low density material. So we don't want to ship around this material around the world, but co-locate these units closer to cement factories, closer to where concrete is being made, and so on and so forth, and thereby make it more readily available. And hence, not only we are inventing or rather putting together our factory with the right IP in it, but we're also talking to prospective customers on licensing models and how do we take it to their supply chain. So we're kind of, again, crossing the chasm from all sides. It's not just solving the technical problem, but also look at supply chain and availability and deployability and so on and so forth.
Right. And is it possible to add it into the concrete mix, or do you need to add it into the cement?
Yeah, today we are following two methods of dispersion. One is called a microencapsulation method, wherein we disperse it and then dry it into a water-soluble polymer. So it's almost like an instant coffee. It is literally like an instant coffee. You put it in water, nothing happens, but give it a shake, and it's instantaneously dispersed. And so that is the route we think will apply directly to like an additive to a concrete plant. And we are still optimizing the chemistry for the encapsulation chemistry so that it doesn't interfere with the cement chemistry. And that's something we are kind of collaborating with the additive companies to kind of arrive at the right mixture. The earlier method I mentioned, where we directly deposit on cement, is very directly applicable to cement factories, and that involves no intermediate chemistry. But however, we are also developing a master batch like approach, where instead of just adding 0.15% to cement, why not add 5%, or why not add even more into like a concentrate of cement and use that as a diluted during your concrete mixing. So instead of when you drop 50 bags of your regular cement, you drop one bag of this, which will carry the nanotube into the concrete system. But these are things which we are developing in collaboration with our partners. We have not yet tested these routes completely because we are focused on developing our nanotube and the properties. And now we are collaborating with people on what is the optimal way to take it to market through the channels of our partners, which could be the leading cement OEMs and concrete companies.
And if we have cement companies listening to this podcast who are interested in this, do you have the potential to work with cement companies in other countries outside the US?
Yeah, in fact, cement and admixture companies, both in the US and outside. In fact, I've already started talking to various regional players as well. And the interesting part is everyone's problem seems to be a different problem, right? Someone has more fly ash than they can use. And how do you use it properly so that it doesn't affect the early strength and the properties? In certain markets like the Middle East, corrosion and things are more important. So, by the way, nanotubes also improve the barrier properties of cement, and thereby reduce the salt intrusion substantially, and thereby increasing the life of concrete. And so that's another element which we have not yet tested in our labs, but I'm quoting from literature. People have done a lot of work, and that has been a focus in areas like Middle East. Besides getting strength and advantages of those, Europe is on a different trajectory on decarbonization. And by the way, the nanotubes are good not only for traditional cement chemistry, but also the emerging cement chemistries, which could even be non-hydraulic, or in some cases, things like the LC3 and so on. It can help as an additive to overcome certain issues like early strength or anything else which these new chemistries might face. Yeah.
No, I think it's a very interesting development, Hari, and I thank you very much for sharing it with us today.
Thanks a lot. Thanks for giving this opportunity. I'm sure I've missed a lot of points which may be relevant, but I think you brought out all of it. And for sure, through your forum and through your association, we will surely get more opportunities to, interact with your members and go into the details. As people say, the devil is in the details, but the opportunity is also in the details. And so I think that's very critical.
Absolutely. Well, Hari, I hope to see you in Dubai again this year.
Oh, yeah, for sure.
Okay.
By the way, the last visit to Dubai was mind-boggling for me. I met a bunch of people from various countries and backgrounds and opened up their problem statements. So it was not one problem statement, but multiple problem statements. And the common goal, everyone was working towards decarbonization. And that is our mission too, is to decarbonize and take the cement industry to where it can be and play our little part in it. And with effective collaboration and with leaders like you who are catalyzing this change, I'm sure we will see it in a very short time. Yeah.
Well, Hari, it's always nice to hear people appreciate the conferences. As you can imagine, they're a huge amount of work. But if they create the kind of results that you mentioned there, then it's worthwhile. So thank you very much for talking to me today. And I look forward to seeing you soon.
Yeah, thank you.
Bye-bye. Thanks for listening to the Clinker Factor podcast today. If you've enjoyed it, do subscribe. And please recommend us friends and colleagues and anyone else who you think would be interested in what's happening in the cement and concrete industry around the world. WCA is a not-for-profit company. Please visit our website to see the services that we offer